This module is about Wi-Fi. And Wi-Fi will be covered in 2 modules, actually, minimum. And this is 2 parts. First part is basics. So this part is just general about Wi-Fi. And then the next module goes into more detail of how A, B, G, C, and everything else is different. Okay? So we'll talk about features, physical layers, MAC, architecture, frame format, and all that. Okay? So what is the difference between 802.11 and Wi-Fi? Right? When you go to a store, you don't find 802.11. You ask to Best Buy guy, can you give me a 802.11 something? They will say, what is that? Right? You say, I need a Wi-Fi access point. They will give it to you. And so the reason is Wi-Fi actually is a trademark of Wi-Fi Alliance, which is nothing to do with the IEEE, but in a strict sense, it's a different organization. IEEE makes 802.11, and Wi-Fi is a group of companies. Wi-Fi Alliance is a group of companies that got together and said, look, this standard is very difficult to implement. Why it is difficult to implement? Because it has hundreds of options. If you implement option number 135 and I implement option number 678, we can't talk to each other. Right? So why don't we decide what options we need to implement? And so they are interoperability group. Right? So every time, and basically they're more than interoperability group because they are the one who put all those options in IEEE in the first place. So they sit down and so they're different from IEEE. IEEE is a standards bodies and they make a standard. In this standard, the standard practice is to accept everything. You want A, I will give you. You want B, I will give it to you. You want C, I will give it to you. Everything is there, but not everybody is going to implement A, B, C. Right? So these other bodies decide whether we implement A, B, or C, or B and C, or whatever subset we implement. So Wi-Fi is that. So when you buy a Wi-Fi logo item that says that this will work with another Wi-Fi logo item, regardless of the manufacturer. So that's why you only buy Wi-Fi equipment and not 802.11 equipment, because 802.11 I could implement and you could implement and we could not talk. Is that clear? And wireless fidelity. Fidelity simply means that, compatibility. And if you want to know about Wi-Fi, you go to wifi.org. If you want to go to IEEE.org, you will find 802.11. Okay? And so I said everything about the Wi-Fi. Now, IEEE has a numbering system, so we will be using lots of these. I want to make sure that everybody is up to date on how these numbers, what these numbers mean. So 802, some people think that 802 represents February 1980 when the first IEEE Standards Committee was formed. I was there at that time. First IEEE Standards Committee was formed for Ethernet, and they call it 802, 8002 something, whatever, 82. And then lots of other committees were formed. Okay, 802.1 is the basic that applies to all of the 802s. So you will have 802.3, this Ethernet, 802.11 is Wi-Fi, 17 is RPR, 16 is WiMAX, and there is a whole list which we'll see soon. But regardless of what 802 number you have, all of these 802s follow common standards. They all have the same security mechanism, 802.10. They have the same management standard, 802.1. They have the same bridging. They have the same logical link control, and so on and so forth. So the 802 is a group. And if you want to be part of 802, so any standards which starts with word 802, number 802, they have to follow all these common things. Okay. So 802.11 follows 802.1 and 2. That's it. 1 and 2 are common. 3 is not. 4 is not. And 3, 4, 5, 6, 7, they're all different. Right. Now, in 802.11, there are many groups. So 802.11, and then we will talk about today about those groups. Those are subgroups. And so basically, while in the marketplace we say Ethernet, in the IEEE it is 802.3, in Wi-Fi is 11, WiMAX is 16, and so on and so forth, right? That's the standard. And there is generally a letter after these numbers. So 802.11.I, that means the ith subgroup in 802.11. They have several subgroups. And so they will apply to this will apply to all 802.11 devices, but they will not apply to other 802.11 devices such as 802.15. 802.15 is independent of 802.11. They don't have to follow the same security method or anything like that. Right? 15 is Zigbee and all that. They follow 15. Wi-Fi is different. So standards with now there is a case, uppercase and lowercase. So A, B, and you have to be careful from now on, because before this you didn't know what the letters case means, but they're case sensitive. Uppercase means this is an independent standard and this will stay forever. So 802.1 AB is independent standard, whereas little like I or W, these are temporary. These will be there for some time and then they will get merged into the base standard and they will disappear. So 802.W, for example, 2001 was merged with 802.1D 2004 and now it no longer exists. You cannot find it in IEEE. Okay, the uppercase survive, the lowercase get merged. So we call the lowercase as amendments. They are changes. Right? Uppercase are the base standards. And if there is no case, then it is a base standard. For example, 802.11 is a base standard. So 802.11 little I could be merged with 11. Right? In the beginning, and the numbers are standard serially, such as 1A, 1B, 1C, 1D, 1Z. When they ran out of Z, then they were AA, AB, AC, AZ, and then BCA, and so on and so forth. So they go by the sequential number. But now they have actually made it slightly change, and they not only use these, like, W was merged with D. Now, if this W were to be done again in this time frame, they would call it 802.1 D little a or B or C or something like that. So they now use like this, 802.1 QAU. So this is Q is the base standard, and this AU is the amendment. And at some point, that amendment will go back to the main standard. And the main standard's years keep changing because Q was done at some time ago, and now the latest one might be 2011, 12, or something like that. Okay, so the main standard is reissued after a few years, and they make it bigger and bigger and bigger. So 11 now, back to 11. 11 was done in 1997. Original one. But today, if you go to buy, you can't find 1997, you will find 2012. So 1997 one had 1 and 2 megabits, only 2 speeds. The newer versions now, newer amendments allow it to run at higher speeds. All versions use license exempt spectrum. So when I was working for WiMAX Forum, and we were very particular about what terms we use, license exempt means that you don't need to get a license. And unlicensed means it is illegal. So basically, if you use unlicensed spectrum, means you are using somebody else's thing, right? But now I was very particular to teach my students, please don't use the word unlicensed, use license exempt, okay? But now people don't know all that. So I see the literature from the marketing people, from the companies that have given up on that request. So today, unlicensed and license exempt are used synonymously, but really license exempt means you are legally using it, you are exempt from license, right? And there's a license spectrum, there's license exempt spectrum, right? If you use illegally, then it is unlicensed. So anyway, so you understand the difference. From now on, try to use license exempt when you're writing something. Yeah.
Would those generally be low range, high frequency?
No, I will come to that. No, at all frequencies. The license exemption is available at many frequencies. All right, so there is license. Need ways to share spectrum along multiple users. And so whenever they give you this much band, they say, okay, this much band is license exempt. Then they will say that means that you cannot just hog it. You have to be able to share it with everybody else. Right? And so in Wi-Fi, they used spread spectrum. Now, the reason I defined spread spectrum before is that now I don't have to worry about it. You know what is spread spectrum. Hopefully, you still know. Okay? Spread spectrum. 3 PHYs. And this had 3 physical layers, 802.11. One was direct sequence spread spectrum. Now, I suppose you know, remember that one too, direct sequence spread spectrum. And the second was frequency hopping. And third was infrared, diffused infrared. Now, most of you probably don't remember infrared, but your remote controls use red light, which is infrared. Actually, it's not red, it is infrared. It is close to red. Okay? And so previously the computers used the same frequencies. For short distance communication, they had a red thing in the back. You could put the two computers in line with it, or you could align your computer with the printer, and it will tag infrared. We don't no longer use that anymore. But that was in 1997. It supports multiple priorities, supports time critical and data traffic. So it also supports time critical application and allows power management. So these nodes can sleep when they're not working. All right. So these were the features. Now, question is, what is license exempt? License exempt is called ISM bands, industrial, scientific, and medical. Now, the application is not limited to these. So if you have an application which is not industrial, not scientific, and not medical, there's no definition for these. So everybody uses ISM bands. Just the name came about because when they first allocated that this is for scientific and medical applications. And there are many bands, and there are different countries have different bands. So there is this band, this band, this band, and so on and so forth. And some of them are available only in Europe, some of them are only available in America, but the ones that are available worldwide are obviously more used. Right? And so most commonly used one is 2.4 gigahertz, right? The one that is used for Wi-Fi. 2.4 gigahertz, and it goes from 2.4 to 2.5, and so there you have 100 megahertz available. Then when that got filled up, right now, you can't really run anything because everything runs at 2.4 gigahertz, are your phones and, the cardless phone and everything else, including microwave. So people moved on to higher one, 5.7 to 5.8 gigahertz, and there we have 150 megahertz available. Okay? So now you know two bands, 2.4, 5.8. When I say 5.8, I mean 5.725 to 5.875. When I say 2.4, I mean 2.4 to 2.5. Okay, that answers your question? Okay, so they obviously started from the low frequencies, but there were just not enough bandwidth here. Right? Here you have some respectable bandwidth to use, do some data transmissions. So now we did what they did was they divided the channel into 5 megahertz channels. They divided the band into 5 megahertz channels. 5 megahertz channels. 5 megahertz. So let's say first channel starts here, 5 megahertz, another 5 megahertz, 2, 5, 5, 5, 5. So given 100 megahertz, you will get 20 channels. So actually, you don't have 100 megahertz. The numbers previously were slightly rounded off. What you have is somewhere around 2400 to 2483. So you have about 80 megahertz. So you'll probably get 16, something like that, right? But Wi-Fi decided to use 20 megahertz. That means they will use 4 channels at once. So when you use one, you use 1, 2, 3, 4. All right, so they used instead of 5 megahertz, they use so. So channel 1 goes for Wi-Fi, goes from here to there. Now then you cannot use these other channels. You cannot really use 2, 3, or 4 because the people at 1 are already occupying those channels. So the next one comes as 6 because you want to leave at least one channel between for overflow. So 1 and then you use 6. And then 6 goes to 7, 8, 9, and then you don't use 10, so you use 11. So you basically have choice of 3 channels. When you divide this, when you program your access point, you can either take 1, 6, or 11, right? You know that, right? Everybody knows that 1, 6, and 11. Now you know why. Because you are using 4 channels at the same time. When you say 6, you are using 6, 7, 8, and 9. All right. When you say 1, you are using 1, 2, 3, and 4. So instead of 20 or so, we have, or 16 or so, we have only 3 non-overlapping channels. You can use overlapping channels, but then you will have a lot more interference. Okay. In fact, you can use the same channel. I can use 1, you can use 1, and we will both be happy, except that we will be colliding once in a while, and you will be retransmitting, I will be retransmitting. Yeah. 5 is why 5 is a channel and 20 is a channel. Yeah, so the channels are numbered. So the thing is, channels are numbered by FCC. FCC is the Federal Communication Commission or something, which is the one in the United States which gives out all these exemptions, right? So they said, okay, we give you 2400 to 2480 megahertz exempt from licensing. And so the channels are, 5 megahertz, by that number they have, these channels, right? But Wi-Fi arbitrarily decided that we are going to use 20 megahertz at a time. We can't do anything with 5 megahertz. So we are going to use 20 megahertz at a time. And because of that, we can only use 1, 6, and 11. Yeah.
But if you say there are 4 channels, then you use 1, 2, 3, 4. And then if you start at 6, you're saving 5.
And we are saving 5 because we just don't want to be, the thing is, when you use 4, you're really using part of 5 and part of 3 a little bit, And so if you leave unclear, you just leave 1 and then go to 6. There is always an overflow. Okay? All right. At 5 gigahertz, there is more spectrum available. However, again, if the channels are numbered like this, so 1, 2, 3, 4, 5, and then up to here, and then they go 36, 37, 38, 39, each of them 5 megahertz. But again, we don't use 5 megahertz, we use 4 at a time. So what you get is 36, 40, 44, 48, things like that, and so on. So basically, you will get some multiple of 6 or multiple of 4 or something like that you will get. And so there are 12 non-overlapping channels. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, and 4. 12 non-overlapping channels. That's all we have. Actually, here is another interesting thing I noticed. That this is not contiguous. This starts at 5150, goes to 5350, and then it starts at 5725, goes to 5825. So the band was allocated in 2 pieces. Okay, so whenever we say 5.8, we mean any of these. Physical, go ahead.
They are using the 20 megahertz as well?
They are doing what?
The channel.
Right. So that's another thing I noticed is that they're using 20 megahertz and they're contiguous. They're not leaving that one which is left here at the lower band. So the 36 and 40, just 4 apart. 40 and 44 is 4 apart. All right. So we already talked about the 5 physical layers, and the first one, the 2 PHYs, 3 PHYs we talked about, right? The 2 PHYs which were wireless. The third one was really infrared, which is totally different. Light, actually, infrared is light. So the 3 which were radio, the 2 that were radio, they were at 2.4 gigahertz, right? and they were operating at 1 and 2 megahertz, and so they said this is not good enough. So they started working on higher speed, and in '99 they came up with two new ones called A and B. A was running at 5 gigahertz band at 54 megabits using 20 megahertz using OFDM. So now you know why I explained you OFDM so much, because we are going to use it all the way through. So if they used OFDM and 20 megahertz, same speed, same band, but they produced 54 megabits per second. However, they had changed the band. And the B guys, what they did was they produced only 11 megabits, and they didn't use OFDM. Okay, they probably just changed the coding something. We'll see in a minute. Okay, so they could only go to 11, 5 times, whereas these guys, for the same band, now these guys can go from 1 or 2 to 54, such a high factor. Right? So once B came about, people loved B more than A because B has the same band. If you change the band, you need all new radio circuitry. Right? So people didn't want to jump to 5.8. So they said, we love B, but it is not fast enough. Why can't we use the A technology at 2.4? So that resulted in G. G is basically using OFDM at 2.4. All right. So much about A, B, and G. So now you know 11, vanilla, which you don't use anymore, and then we have A, B, and G. And you don't generally, we didn't use, now we are using A, but mostly we didn't use A for a long time. We just use B and G. Yeah.
Are most consumer electronics, so that to use Wi-Fi, able to use either the 2.4 or the 5.8?
Yeah.
Okay. Is that a standard that all of them should be able to use both, or?
No. Not all of them should be able to use both. In fact, most of the equipment uses only one. And some use both. Of course, they are more expensive. And the thing is, now these things are not cheap. These are $500-800 equipment. So they can use both. Right? Yeah. If it was a cheap phone, it will probably just do 2.4. Okay. All right. So there is another problem with Wi-Fi. And actually, I might say Wi-Fi and 11 now, basically with wireless, that there is a hidden node problem. You cannot use the Ethernet method called CSMA-CD. Because in CSMA-CD, what we do is carrier sense multiple access collision detection. Collision detection, CD, is the part that you cannot do here. Why? Because we cannot detect collision. So here's the thing. You see, in this scenario, A can listen to B, and B can listen to C, but C cannot listen to A. Right? And so what will happen is if both A and C transmit to B, they cannot detect collision. They cannot detect collision. Sender cannot detect collision. Only receiver can. Right? So in Ethernet, this is how we operate it. Basically, the sender detects the collision and stops. Right? We cannot do that here. And so the receiver has to tell the sender that please stop. And therefore, this is called CSMA-CA, collision avoidance. However, actually, we don't even use collision avoidance. All we do is we just don't speak until the receiver says you speak. So there are 4 packets for each packet that you want to send. So this guy wants to speak to the access point. It says, I am ready to send. Can I please? This one says clear to send. Yes, you can, because nobody else wants to speak right now. Then it says, okay, here's my data. Then it says, I got it. So 4 packets are sent for every packet that needs to be sent. On Ethernet, this will be just 1 packet. Yeah.
That's just one data packet? You can't be clear to send, a couple of them?
That will come soon.
Okay.
Yeah, that will come soon, but this is the original one. So basically, there is a 4-way handshake here that for every packet, now I want to send this packet number 2, You so do the same thing. You say RTS, CTS, data, and ACK. Third, RTS, CTS, data, and ACK. Because it is quite possible that two people want to speak and they will send RTS and they will collide and nobody will send. But at least the data is not lost. RTS is very tiny, right? So you just lost maybe microsecond. But if data could be long, and if you collided in the middle of the data, you have to retransmit the whole data. So at least you don't retransmit the whole data. You just send RTS, and you get a CTS, and you get ACK. Those three other packets are very small. Okay? All right, so that is what MAC is. MAC is Media Access Control. And the Media Access Control is CSMA-CA, which means that CSMA. So there is still carrier sense. So you don't even send your RTS if you hear somebody else. Right? And so carrier sense, you sense the carrier, you listen to the carrier, and if somebody is speaking, you don't. CSMA is there. But how do you get collision? You avoid the collision by asking the receiver. Right? So listen before you talk. Collision, carrier sense multiple access means listen before you talk. If the medium is busy, then you back off, you draw a random number, and you say, okay, I will try again after such time. If two people collide, they will both draw a different random number and start at a different time. So avoid collision by sending a short message, RTS. RTS contains several information. So RTS says, look, I want to talk to B. I want to talk for 10 seconds. Duration, of course, it won't be 10 seconds. And I want to talk for 10 milliseconds, maybe. Duration of the message. And then, so everybody listens to it, as many people as they can listen, and they will all know that once this guy starts, he's going to be there for 10 seconds. Right? Destination sends clear to send, and whoever is the destination, most often it is the base station. The destination says clear to send. And then in that also it repeats the same thing. Every packet actually has the remaining time. It says, okay, so in the RTS, it will include the time of the RTS, time of the CTS, time of the packet, time of the ACK. In CTS, it has the time of the CTS and the packet and the ACK. In the packet, there's the time of the packet and the ACK. In the ACK, it says, I am done. Right, so the time is there in every packet. So because you cannot detect collision, each packet is ACKed and MAC level retransmission if not ACKed. If you don't get the ACK, start from the beginning. Okay, so clear as to how the access control works? Yeah. Request to send collide with some other request to send? Yeah, that's what I said. Basically, they will both not get the CTS and they will both draw a random number. No, there's no CDMA. Collision, okay, CDMA means code division multiplex access. I'm not talking code CDMA here. They will both draw a random number, not like, okay, I see what you were going from. In CDMA, I said that in frequency hopping, you change the frequency by using a random number generator. Here, we are not changing the frequency right now. We are just saying that we draw a random number to decide how long to wait. Okay, this is the same thing that is done in Ethernet too. If you remember Ethernet, if you collide, then you draw a random number and you back off. Anybody remembers that? Right? Exactly the same algorithm is used here. You draw a random number and you back off. Back off means you wait for a time. You don't change your frequency or anything. You just back off in time. All right. Now they also do more than priority. So what they do is there are three kinds of time you have to back off. Time you wait. One is the initial interframe spacing. So between one frame and the other frame there is a space, and so that could be short, which is SIF. It could be medium, which is called PIF, or it could be large, which is DIFs. So some very time critical thing, such as RTS, CTS, and ACK, these has to be sent right after one CIF. Very small period, and you send it right away. Okay, this is first. Data, after data has been sent, the acknowledgement is the highest priority thing. It has to go. After RTS has been sent, CTS is the highest priority thing. Okay, so they start within 1 CIF of the busy period ending. As soon as the busy period ends, within 1 CIF of them, we send these. Then there is a small period allowed during which there is a pre-reservation PIFs, point coordination function. This simply could be better remembered as periodic coordination function. So periodic means something that you have to do every second or every millisecond or something that repeats. For that, you make a reservation that I want to speak 2 words every second, and you get a reservation for that. And so that you can do during this time. Yes. You will have a reserved point that as soon as the CIF is over, then after 3 milliseconds, your time. Then after 4 milliseconds, your time. So you will have a reserved spot. DIFs. And after DIFs, everybody else can do, and that is called, DIFs is the distributed coordination function. And then you basically go back and then try your luck. There is no reservation then. Best effort. Then basically you send your RTS. If it makes it, good. If it doesn't make it, back off. So 3 kinds of traffic. First is what we would call the control packets, which are RTS, CTS, and AC. They go in CIFs. Then time critical traffic, we call it PIF, point coordination PCF. They go in the reserved slot. And then DIFs is the distributed coordination function, which is everybody else. No reservation. Is this clear? So basically, after every packet, this thing takes off, right? Now, so what happens is the access point starts the whole cycle. It sends a beacon. It says, okay, start fetch. Okay. And so for some small period of time, there is a PCF access, contention free access. During that time, whoever has reserved can send. And then after that time, contention access. Whoever has not reserved can try. So that is clear, right? So there is a beacon, and the beacon has more than timing. Beacon also has the name of the base station, and it might even have that, other things about that. This is Wushtel this and Wushtel that, and so on and so forth, right? So now back off. So there is only one queue in the stations, and therefore whatever is the head of the queue will decide what kind of access you need. You either need periodic access or you need them. You need time critical and so on, whether you want to send a packet or acknowledgement or control and so on and so forth. And you keep 3 variables: contention window, backoff count, and network allocation vector. It will become clear as to how we use that. So if a RTS, CTS, data, or anything is heard, then you take the time from that frame and put that into your nav. Nav is actually your timer. So you set your timer, and this says that I'm going to talk for 10 seconds. You set your timer to 10. Now don't disturb anybody for 10 seconds. Right? Now when the timer goes off, then you can say, let me see, is the medium now available? Now it's quite possible somebody else has grabbed it before you. Right? But then, basically at that time, you listen for the next timer value and say, okay, this guy is have for 11 seconds. I'm going to set my timer to 11. So nav is basically a timer. Okay. Now back off and contention window is basically, how many times you have backed off. If you backed off first, you back up between 0 and 1. Then you back up between 0 and 3. Then you back up between 0 and 7. So more and more time you try, the wider and wider you have to wait, because there might be a lot more people trying it out. Okay. First, we assume only 2 people are trying, so we go between 0 and 1. And we both try a random number between 0 and 1. You probably try 0, I try 1, and we are both happy because you go right away. I have to wait for 1 slot. right? But it is quite possible 4 people are trying. In this case, we both draw 0 and 1. 2 people draw 0, 2 people draw 1, and they all collide. And then in this time, they all have to draw between 0 and 3. So this is exponential backoff, just like in Ethernet, right? Every time you try, you double the range. Double the range, okay? And I think that would be a good slide to stop. Okay, I will stop right there.